Hello, this is Fatemeh Ansarizadeh, a PhD student at Deakin University. Today I'm presenting my paper regarding graph neural network. To commence the presentation, I provide a brief introduction to the field we are focusing on. Then a brief background knowledge of graph neural network is explained. In the next step, I explain the method that we put forward and the novelty in it. After that, the result of our experiment on citation and knowledge graphs are represented and compared by previous results. At the end, I wrap up the presentation by a brief summary and conclusion of our work. Conventional methods were focusing on structured datasets, like an image, which can be represented in Euclidean space using a lattice. But in reality, more than 80% of collected data in nature is unstructured. In such cases like text, audio, and video, we need non-Euclidean space. That's where the importance of using graph shows itself. So we use graph for analyzing such irregular domain. Graph has two important features: node or entity and edge or relation. Adjacency matrix, which is an square matrix, represents the relation between these entities. Using this adjacency matrix, identity matrix, and degree matrix, we can form the normalized graph Laplacian matrix, which has interesting features as written here. The basis of our method roots in a spectral convolution. Here you see how we can convolve a signal with a filter in both Fourier and vertex domains. In reality, we prefer to simplify it by using Chebyshev polynomial. After that, we consider some simplifying assumptions for parameters in order to prevent overfitting. If we consider multiple channels of input and show it by capital X, we can convolve it by filter G to have the output. Function f here represents nonlinearity. Since the given Laplacian leads to instability in practice, it will be replaced by a symmetric Laplacian, which leads to a layer-wise function, where sigma represents activation function. Obviously, the given input can be considered as what we have initially in layer number 0. Considering the definition of Laplacian and the relation between eigenvalues of Laplacian and eigenvalues of adjacency matrix, we can find diagonal matrix form of these two eigenvalues. Then using definition of eigenvalues and eigenvectors, we can find the relation between adjacency matrix and eigenvalues of Laplacian. Considering the spectrum of normalized Laplacian matrix, which is between 0 and 2, and the relation between lambda and mu, we can find the range of mu, which is from -1 to 1. From graph signal processing viewpoints, the frequency response of 1 plus mu is corresponding to low-pass filtering because it has its highest value when lambda equals 0, which is the lowest frequency. To modify the original formula in order to have our proposed technique, we replace A hat by a new matrix which is concatenated form of A hat and B hat, where A hat represents low-pass filtering and B high-pass filtering. Please bear in mind that A hat and B hat are row normalized. Then weight matrix also should be concatenated vertically to form compatible matrices. Here delta is multiplied by low-pass filtering and gamma multiplied by high-pass filtering. Initially, the input is given to the first convolutional layer, and the results are fed into a ReLU function to add some nonlinearity. After dropouts, the result will fit into the second convolutional layer, and at the end, a softmax will do classification. In order to observe the performance of our proposed technique, we chose two famous citation network datasets, Cora and CiteSeer. It is worth noting that Our experiment setting and hyperparameters have been chosen exactly the same as what Keith mentioned in his paper. We can find it in reference number 1. This table represents our result using both high-pass and low-pass filtering and compares it by the result of Keith, where he was simply using low-pass filters. As you see, in both Cora and Size2 dataset, we have a slight enhancement in accuracy of classification by combining high-pass filter with low-pass filter. In the next step of our experiment, we choose a knowledge graph dataset. In this case, we are working on WebKB, which is consisting of 4 other datasets. Here, the proportion of the number of edges to nodes have been given. This table represents the result of our method when we are working on knowledge graph and compares it by what we can get using GCN method, what Keith mentioned in his paper. The result reveals that this high-pass filtering is not only helpful for citation, but also it works for knowledge graphs. Another point that this result can reveal is the dependency of density of graph to the enhancement of accuracy of classification due to using high-pass filtering. For example, Cornell dataset has the least density, and as you can see in the table, it has the least, which is almost 0, improvement in classification when we use high-pass filtering as well. On the other hand, regarding Washington, which has the highest enhancement, you can see that it has very high density. In this work, we presented a new method which can integrate low and high-pass filtering into convolutional layers, which is quite general and can be used for both directed and undirected graph. The result of our work revealed that there must be some relation between density of a graph and the enhancement that we can get after introducing high-pass filtering. The Keith paper that we were considering as a source is mentioned here, and other references represent the datasets. Thank you.